This is the review of the EPS modeling and energy costing analysis workshop. So in this exercise, we have here a network, okay? This network is supplied by reservoir number 1, and then water is pumped through two different pumps through the network, okay? In this exercise, we are considering three different scenarios that represent three different solutions that we are proposing. One of the solution is this one, okay, that we call the tank control scenario, where we have water coming from reservoir number 1 and pumped to the network, where we also have an elevating tank downstream. Okay, so this tank is also able to provide and supply gravitically the distribution network when the pumps are turned off. We have then defined another scenario that we called the scenario with no tank constant speed. Okay, in this case, as you can see, when we move to this scenario, the tank and the pipe that connects to the tank is with gray color. This means that these elements are inactive in this scenario. Okay, we can we can represent this in another way. So if you go to more tools options, okay, we have here a checkbox in order to not display inactive topology. Okay, if I uncheck this, all elements that are inactive will disappear. Okay, so if you want to have inactive elements with a gray color so that you know that, okay, they are not in this scenario but they are active in other scenario, you can keep them with a gray color. If you think it's better to simply disappear them from the drawing, you can disable the Xbox. Okay, in this case I will turn this on. Okay. So in this scenario, we have a no tank and we have constant speed pumps. This means they are normal pumps that have always to be turned on in order to supply the network. Okay. So we also defined a third scenario to analyze a third solution. Okay. In this case, we have also a no tank downstream, but we have considered a variable speed pump. Okay. How we define this? So if you click twice on the pump, it opens the property editor, and we have here a field that is called isVariableSpeedPump. In case we want to model a variable speed pump, we have to define this field to true. Okay, and then we have to define exactly how this pump will work. Okay, variable speed pumps work and can work depending on in order to assure target head downstream, or in order to assure a fixed flow, to deliver a fixed flow, or based on a pattern based of the relative speeds. Okay, so we have these three options, and this is how the variable speed pumps work. Basically, they will try to adjust their relative speed because they are variable speed pumps. They can change their variable speed in order to assure a fixed flow or a target head downstream. Okay, with normal pumps, you cannot do this. They cannot change their variable speed. So basically, the speed of the normal pumps will always be the same, and the flow will change, and also the pressure downstream will change depending on the flow in the demands of the network. Okay, in this case we have chosen as a control for this variable speed pump the field target head. Okay, we are saying here that we want our pump to work in order to assure a constant head downstream at node J1. So J1 is our control node. We want to assure a constant target head of 380 feet at J1. So basically pump number 4 will change their speed, their relative speed, in order to assure always the same head downstream. Okay. If we move again to the no tank constant speed scenario, and we click on the pump number 4, we can now see that the variable speed pump field is turned into false. Okay, this means that we don't have here variable speed pump. It's a normal pump, and basically the flow on this pump will change depending on the demands of our network. Okay, the goal here is to understand which one of these three scenarios it's more economical. Okay, so we will do this analysis. In this workshop, we are seeing already here the solution. So you have already entered all the data for the pumps, all the controls for the pumps, and now we have to just compute these three scenarios. Okay, so we are computing EPS scenarios. So a EPS scenario means extended period simulation, and we use this type of simulation when we want to model the conditions along a period of time, more than an instant. Okay, so if we go to the options, here we have a field to choose if we want what type of analysis we want to do. If you want to run a steady state or EPS. Steady state is just an instant of time. Usually we use this for design, for the worst case conditions when we want to design the network for peak flows. The EPS allow us to understand how is the behavior of the network along a time. It can be a day, 2 days, 3 days, the time as you want. Okay, so we have configured three different scenarios that will run in extended period simulation over a period of 24 hours. So let's compute the three different scenarios. We can compute all the scenarios by clicking on batch compute, and then the scenarios will all the scenarios will run at the same time. Okay. And now we can try to understand the differences between each one of the scenarios. Okay. Before entering into the graphs and into the reports, just to tell you that one important thing that we need to insert for the pumps is the pump curve and the pump controls. Okay, so for example, here when we are on the no tank constant speed scenario, if we click twice, we have here a field for the pump definition. Okay, where we have to set what is the pump curve. Okay, the pump curve is defined based on these different types that we have in WaterGEMS. So basically the standard 3-point that is what is defined here. We have to define 3 points of the curve, and WaterGEMS will compute the curve for us, the rest of the curve. The 3 points that we have to define in this case is shut-off flow. So when the flow is 0, what's the maximum head of the pump, the design flow and design head of the pump, and also the maximum operating point, okay, where we have the maximum flow with 0 head, shut-off head. So if we know these 3 points of the curve, then WaterGEMS will compute all the curve for us. We can also choose other options. So for example, the design 1 point is when we just have 1 point. Usually it's the design point of the pump, design flow and design head, and the WaterGEMS will compute all the rest of the curve for us. Okay, usually we choose this for preliminary design when we have not yet decided which pump to install. Okay, if we want to assure much more accuracy, okay, maybe we should choose multiple point when where we should insert several points of the curve, so that the curve that is computed by WaterGEMS it's much more near the reality. Okay, so the pump curve, it's very important, we have to define it. Although it's a normal pump or a variable speed pump, we have to define the pump curve. Okay, so this does not depend on the type of the pump. So you can see here that we also have the definition for the variable speed pump, and also for the scenario with tank. Okay, we also have the definition of the pump. And another thing that it's important to define is for the scenario with the tank, we have to define exactly how the pump will work. So basically when the pump will turn on and turn off. Because we have a tank downstream, we are able to turn off the pump when the tank is filled, and then the tank will be able to gravitationally feed the network. Okay, so this will save us some energy with pumping. So we can click on the pump, and for example, we have a field for the controls. So it's here, and if we click here, we can understand how this pump is working. So basically, pump number 4 will turn on. This means that pump number 4 will turn on when the hydraulic rate at the tank T1 is below 350. Pump number 4 will turn off when the hydraulic rate is above 359. Okay, so this is how pump 4 will be turned on and turned off. We can also go to pump number 5 and it's the same. Okay, um, so basically it will turn on and off also based on the tank's level. Okay, so for the no tank scenarios, okay, constant speed and variable speed, because we don't have a tank, we have to, the pumps have always to be turned on in order to assure the supply to the network, right? So now we are ready to make some analysis. So some interesting analysis, we can see, for example, how the pressure change in the network for the three different scenarios. For example, for J1 and J3. Okay, let's select J1 with the control button of the keyboard and at the same time selecting J3. With the right button of the mouse, we select graph. Okay, and then we can select to see pressure. Okay, so basically this is for the tank control scenario. Okay, and for the tank control scenario, we can see that when we have a tank, the change in pressure in J1 is much higher, okay, because it's immediately downstream the pumps, and node number 3, the difference is smaller, right? Why? Because here in this case, we also have a tank near that is able to supply the network. So the tank is working as trying to balance pressures in the network. That's why also the changes in pressure in J3, it's smaller than J1, okay? It's more far from the pump and we have the influence of the tank, okay? We can also see in the same graph the results for the three different scenarios. So if I click just in J1, right click, and now graph, I can select to see the difference between the three scenarios. So I select here three scenarios, and now, okay. And now I have the results here for the three scenarios. So basically, when I have a tank, the pressure at J1 changes a lot, as you see by the blue line. When we have a tank with variable speed, you can see that the pressure at J1 is always the same. It's 380. And why? Remember why? Because we set this pump as a variable speed pump, and this pump is working to assure the same target head at node J1. And this target head is 380. That's why we have always the same value of head in this node. Okay, and then we also have scenario number the other scenario, no tank but with a constant speed pump. In this case, we have higher pressures at J1, okay, because we don't have the effect of the tank, okay, to balance the pressures. But in this case, the pressures change between 410 and 430, okay. So this is an analysis. We can go also to node J3 and do the same. Click graph. Okay, we can see hydraulic rate or pressure. Let's now see the pressure. Select the three different scenarios. Click OK. And now we have here differences for the three different scenarios. So basically, when we have a tank, okay, we can assure smaller pressures at node J3. Okay. Here, okay. That's why, because we have the influence of the tank balancing the networks, the pressures. Okay, when we have when we don't have tank, but we have a variable speed pump, also the pressures achieved at node J3 are not so high. Okay, so basically pressures are higher at this node when we just have a normal pump. And now that we have seen, for example, pressures for these two nodes, we can now try to understand what are the costs of which one of the solutions in order to try to understand which is more economical. Okay, we have here a tool that is called energy cost analysis, okay, where we can define the costs per each scenario. Okay, so if I open the energy cost scenario, I can define what scenario I want to compute the cost. So let's start by the tank scenario. Okay, I click here and this will compute the costs for this scenario. Okay, so I have here a description of all the costs, so the total costs. So basically in kilowatt hour, in money, volume. One thing that we want to look at is the daily energy cost. Okay, so the daily energy cost when we have a tank is 690. Okay, we have also much more details. Of course, you can change here in these tabs, and we can also see details for the pump. So for example, if I want to see pump number 4, I can see the results in detail for each time step for each pump. So basically, this is for pump 4, and this is the flow pumped by pump 4. Okay, we can see that some time of the day the pump is turned off, where we have zero flow, and we also have the efficiency of the pump at each time step, the energy consumed at each time step, and also the cost. Okay. Can go also to pump number 5 and see the same results. Here we can see the pump number 5 is always turned off when we have the tank installed. Okay. So now we can also try to change this and go to the no tank constant speed. So when we have a normal speed, a normal pump in our network with no tank, the costs increase to 985. It's much more than the 690 that we had before. And also we can see the details for the pump. Okay, so in this case, remember, because we don't have a tank downstream, the pump 4 is always turned on. Okay, and pump number 5 is turned off. Okay, so pump number 4 is enough to supply the network. Okay, and now we can change to the no tank variable speed pump. Okay, compute, and now the total energy cost is 729. It's less than the previous scenario where we have a normal pump, but it's more than the scenario where we have a tank installed. Okay, so why this result? Variable speed pumps usually are much more cost effective than normal pumps, because as they are able to change this relative speed, the pump curve of these pumps also change, and then they can assure better efficiencies at different with different operating points. In the case of the first scenario with the tank, this is the most cost effective in this case if we are looking just at daily energy costs, because it's the only scenario where the pumps can be turned off during some parts of the day. But if we want to make a complete analysis, we have to look more than just the daily energy costs. So we have to consider also the investment costs. In this case, adding a tank to the network, if it's not already there, adding a tank to the network is a big investment, right? So if we consider all the life cycle costs, including the investment of the tank, probably installing a tank can be more expensive solution. So in this case, we have to analyze all the variables, right?
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.